the next lecture on wireless communications. Today we will look at yet another class of error control codes called convolutional codes. First, the outline for today's talk. We will start with an introduction to convolutional codes, which are essentially codes with memory. We will talk about trellis codes, followed by Viterbi decoding, which is the standard decoding procedure for trellis codes. And then we will have a brief peek at trellis coded modulation, which is an attempt to combine error control coding with modulation. So, this is the brief outline for today's lecture. So, let us see what we have learnt so far. We have talked about cyclic codes in our previous lectures, and before that we discussed the linear block codes. We have also realized that cyclic codes form a subclass of linear block codes and BCH codes form a subclass of cyclic codes. We also studied Reed-Solomon codes, which are again a subclass of BCH codes. We talked about the encoding process for all of them. We learnt how to make the generator matrix and generator polynomials for these codes, and also some fast decoding procedures. Specifically, we discussed the primitive element concept, the primitive polynomial and minimum polynomial required to construct the generator polynomials for Bose-Chaudhuri-Hawk-Wingham codes called BCH codes. Then we discussed RS codes. Please note, all of them are linear block codes, but these are essentially codes without memory. The whole philosophy of coding is to add redundancies in a known manner, which is done using linear block codes. However, we can add another dimension to it, which is the memory part. That means the same input bit stream may not be encoded as the same output bit stream if you are ensuring that a memory system with memory is used. For linear block codes, if you have the same input information word, you will always have the same code word. This is not going to be the case. It should depend on the input stream, the state of the memory, and these two will decide what is going to be the output. So, let us talk about the convolutional encoders. First of all, please note that we are going to start with a shift register, the basic memory block. Let us say the number of elements in this memory block is nu, where it is measured in terms of k naught, the information frame. What is the information frame? We are processing certain number of bits at a time, which are being placed inside the memory, and the memory is much larger than the set of bits coming in input to the memory. Then there is a logic element. Based on this logic, you send out the code word frames. Please note that code word frame is larger than the information frame. In fact, k naught over n naught represents the code rate. Now, the output, the code word frame, depends on two things: the input frame or the information frame, and the elements in the memory which have certain bits stored inside them. Together they decide what we are going to output. So, the constraint length of a shift register encoder is defined as the number of symbols it can store in its memory. If the shift register encodes m previous information frames of length k naught, as shown here, the constraint length of the encoder nu is equal to m times k naught. You will find several other definitions of the constraint length in the literature. This is one of the popular ones. Let us look at a simple example of a code with memory. So, we have a shift register with 2 bits, and then we take 1 bit at a time, and we do some kind of a basic processing and output 2 bits. So, the number of bits in the code word frame is 2, the number of bits in the information frame is 1. So, K naught is 1, N naught is 2, and the rate of this encoder is 1 by 2. This is at a stark contrast to the linear block codes, where the N and the K's are usually large, hundreds, maybe thousands. Here we are talking about 1 bit input and 2 bit output. This is one of the fundamental difference. So, here in this encoder, as we discussed, K naught is 1, N naught is 2, and the code rate is half. It is possible for us to construct a state diagram based on what is the state of the encoder, what input comes in, and what is the state transition. Fine. Clearly, there will be 4 states in the trellis that will construct using the encoder shown here, because the states can be 0 0, 0 1, 1 0, and 1 1. There are only 4 possible states. Now, here I am depicting the states 0 0 0 1 1 1 and 1 0 and the state transition. It is fairly simple to note down the current state, the incoming bits, carry out the logic here, and then go to the next state and the outgoing bits. So, it is easy to construct the table and the state diagram. But another way to represent the same information of the state diagram is to use a trellis diagram. What is a trellis? Trellis is a semi-infinite structure, starts from here, but extends up to infinity. It has certain number of states. In our example, there are 4 states 0 0, 1 0, 0 1, and 1 1, and the arrows show the state transition, and the x axis shows the progression in time. So, the philosophy is as follows: each time a bit comes in into your encoder with memory, you always are sitting in some state. Now, 2 things can happen: either the state remains the same or the state changes. In the process, you will send out certain bits which we write on top of the arrow. So, it is fairly easy to understand this trellis diagram, which exactly has the same information as the state diagram, but in a more simplified manner, in a manner in which we want to use the information, in the manner that we have the progression along the time axis. So, if I am sitting at 0 0 and 1 bit input can come in. So, whether a 0 comes in, I move on the upper arm. If a 1 comes in, I move along the lower arm. So, if a 0 comes in, I stay in state 0 0, which is evident because I was sitting in 0 0, and if a 0 comes in, it is a shift register. So, the last 0 goes out, this 0 goes here, and a new 0 fits in, you still remain in the state 0 0. If you look at the state diagram, if a 0 comes in, you revert back to the same state. And why is it coming like that? Because state is represented by what is sitting in the memory. This is your memory. If 0 0 was sitting here and this is a shift register, another 0 comes in, it will push here, this 0 will go here, and this 0 will be discarded. But for an observer, 0 0 state transits back to 0 0. On the other hand, if I was sitting in 0 0 and a 1 comes in, then this 1 will go here, this 0 will go here, the last 0 will be discarded. So, the next state should be 1 0. So, incoming bit is 1, current state is 0 0, the outgoing bits will be 1 1 by logic, and the next state will be 1 0. So, here if you see, if you are sitting in 0 0 and a 1 comes, you take the lower path, the output is 1 1 and the next state is 1 0. So, the dots in the diagram represents the states of the encoder. If I had a 3 bit shift register, I would have 8 states. A 4 bit shift register would give me 16 states. Please Note our observation as before, coding theory for channel coding deals with introducing structure in the code. So, the general philosophy is, if you have a lot of structure, which is algebraic structure in our case, and a noise breaks the structure by changing some ones to zeros and vice versa, then it is easy to identify where the structure was broken and then substitute back and try to do error correction. It is a very layman's version, an intuitive explanation how coding works, but the structure can be only put up at the expense of adding redundant bits. In this case, we add another dimension to the structure. We give a geometrical structure on top of an algebraic structure. This is a very geometrical thing. In fact, certain transitions are forbidden. If you see, if I am from 0 0, there is no way I can go directly to 1 1. I cannot have this straight transition, but the noise does not know this. Noise is random. So, many times it will appear at the decoder that the transition from 0 0 goes to 1 1 because of the random bit errors. Clearly, you can detect it, and you can also look at what is the most probable transition that you should have been through, thereby correcting the error. So, I have added another dimension of structure. That is why trellis codes can be stronger than the linear block codes in certain cases. So, the information contained in the state diagram can be conveyed usefully in terms of the graph called the trellis diagram. In this case, the rate of the encoder is half, because 1 bit comes in and 2 bit goes out. So, the incoming bit can either be 0 or 1, therefore, there are only 2 branches emanating from each node. If 2 bits were coming in, had k not been 2, then you should have 4 branches coming from any node, corresponding to 0 0 bit coming in, 0 1 bit coming in, 1 0 or 1 1 bit coming in. So, why do we use this trellis structure? It seems both encoding, or at least the visualization of encoding, and the decoding is extremely easy using this trellis diagram. First of all, the idea is that you start with the top left corner, the top left node, which is the state 0 0. Depending upon which bit comes in, whether a 0 or a 1 comes in, you choose whether to go on the upper branch or the lower branch. 0 if you want to traverse the upper branch, 1 implies go for the lower branch. And then you go to the next node, and then you can carry forth this kind of a mechanical process. So, if you want to look at a trellis and see that you start with a 0 0, and if a 1 comes in, you go here, and then a 0 comes in, you take the upper branch, and if the 1 comes in, take the lower branch, and if a 0 comes in, take the upper branch. So, what is the input bit stream doing? Input bit stream is telling you which branch to choose. At every bifurcation, you have to take a decision, and the input bit stream tells you which direction you can move. That means we make a very important observation. Any input bit stream corresponds to a unique path in the trellis, because the bit stream is telling me choose upper, lower, lower, upper, lower, and so on and so forth. A different bit stream will let me choose upper, upper, lower, upper, and other. So, there is a unique correspondence between an input bit stream and a path in the trellis, which means if you want to jump ahead and look ahead, we will see the decoding process is nothing but identifying the most likely path in the trellis. So, it is a search of the paths. Question?
In the last row,
Yeah.
there is a third element.
Yeah.
So from that, if the 1 0 is there, it should be the lower one, and 0 1 the upper one.
You are talking about this node?
No, below that node.
This one?
Yeah.
Okay.
So from that 10 is there, then we are going on the 10 state.
Okay, so let us look at this node. The question being asked is, how does the transition happen if you're sitting at this node? What do we mean by sitting at this node? The encoder has the memory elements containing 1 1. That's why the state 1 1. Now two things can happen. Either a 0 can come in or a 1 can come in. If a 0 comes in here, this is in a shift register. The rightmost one will be discarded, the left one will occupy the place of the right one, and a 0 will come in. So, you will clearly go to state 0 1. So, you will go to state 0 1, but what is written on the branch tells you after the logic what is output. Fine. So, in the process, if I were sitting on 1 1 and a 0 comes in, I would go up to 0 1, but what will be thrown out of the encoder is 1 0. On the other hand, if I am sitting at 1 1 and another 1 comes in, my state transition will not happen, but I will shoot off something different. So, coming to the encoding, we have realized that encoding process is nothing but following a particular path within the trellis. Let us look at an example. So, here is a 4 state trellis. Just by looking at the trellis, we can say a couple of things. The first thing we can say is that there are only 2 elements in the memory, hence the 4 states. The other thing we can say is that from every node there are only 2 branches emanating. That means the input frame size is 1, correct? But we cannot say anything about how many bits are being thrown out. Of course, we have written it down that over every branch we have labeled 2 bits. So, n naught is 2. By depiction we have shown that 2 bits are thrown out for every bit that comes in. Right? So, we have been able to identify a lot just by looking at the trellis diagram. So, if you are asked to design a convolutional encoder, it suffices to give the trellis diagram and vice versa. Suppose we wish to encode the sequence 1 0 0 1 1 0 1 using the following trellis diagram. So, we start here, that is the starting point, initialization 0 0, and then the moment we see a 1, we take the lower path, we are in this node. Then the next bit comes in, it is 0, we take the upper branch, and then 0, again we take the upper branch, and then we get a 1, we take the lower branch, another 1, we take another lower branch, an upper branch and lower branch. So, this sequence of bits at the input corresponds to the darkened lines in the trellis diagram. Not only that, I did not have to go and read out or do the calculations and again using the logic to see what will be the output bit stream. I read it off 1 1 0 1 1 1 1 1 1 0 1 0 0 0. That is my encoded output for this bit stream. Question?
Sir, in the previous diagram, can we change the logic?
Okay.
Internal logic.
Yes. So, the question being asked is, for any trellis, this trellis or the previous trellis, can we change this logic? So, the answer is yes. In fact, that decides what is a good encoder and not so good encoder. In fact, what is written out on the branches, what is output, depends upon what is the logic we use. So, here we have used binary additions here, XORs. If we combine not these two, but let alone just this one and this one, then I will get something else on the output, right. We will find out, or we will find a way to categorize which is a good trellis and which is not so good a trellis. But yes, if you change the logic, what you write on the branches will change. So, now let us go back to our encoding process here, and we have observed that any input bit stream corresponds to a unique path in the trellis. So, you can also have a polynomial description of the convolutional codes, and what you can do is represent it in terms of a delay. So, in this simple diagram that we have been using as an example, A and B, let these two be the two output bits. So, A can simply be represented in terms of I and the delayed versions of the I. So, if you look at the logic, A is nothing but I plus a delayed version of I plus two delayed versions of I. So, I n minus 2 plus I n minus 1 plus I n. Whereas the second bit B is nothing but I n minus 2 plus I n for any input bit. So, let the input stream of symbols be represented by a polynomial. Multiplying polynomial by D corresponds to a single cyclic right shift of the element. Therefore, what we can write is G11. What does G subscript 11 imply? Yes, it is the generator polynomial which corresponds how the first bit 1 is associated to the first output bit. G12 represents the relationship between the first input bit, and we have only one input bit, to the second output bit. Had there been two input bits and three output bits, you will have G12, G13, G21, G22, G23. So, this is an efficient way to represent how the input and output are related. The power of D tells you how much is the delay. If you multiply it by D, you increase the delay by 1, you increase the right shift by 1. So, you can define the generator polynomial matrix. Please observe the words. We have talked about generator polynomial before for cyclic codes. We have talked about generator matrix for linear block codes. We are now defining something called as generator polynomial matrix, which basically it has these two components G12 and G11 and G12 here in GD. I can specify my entire convolution code using the generator polynomial matrix. Now, let us have the distance notion, and these are a matter of definition. The nth minimum distance of a convolutional code is equal to the smallest Hamming distance between any two initial code word segments L frame long that are not identical in the initial frame. So, it is a definition. So, what are we trying to do? Why do we need these definitions? We need to know how good or bad is our convolutional encoder. So, the first thing to observe is that any sequence of bits corresponds to a path in the trellis. So, an error will be made when you mistake one path for the other path, because decoding process requires you to pick and choose the most likely path. That means we must have a notion to have difference between the two paths in terms of a Hamming distance. How do you show two paths are different? A convenient measure is the Hamming distance between the two paths, right? If all the paths are very different, they do not resemble each other, then a few errors introduced by the noise will not make one path look like another path in the trellis. That is, you will not mistake one bit sequence for another bit sequence. Fine. So, we need a distance notion essentially to tell you how different two paths in the trellis are. The code can correct T errors occurring in the first L frames provided the Lth minimum distance D star is greater than 2t plus 1. This notion comes directly from our observation in the case of linear block codes. That is, if the two paths are separated by D star distance, then T errors can be corrected in that segment if D star is greater than or equal to 2t plus 1. Same logic. Now, let us define a very interesting concept which is called D free, or the free distance of a convolutional code. The free distance of a convolutional code is given by max dl. The free distance is thus the minimum weight of the path that diverges from the all zero path and later merges back. For a linear code, this holds true. That is, if you are talking about a linear convolutional code, then all distances from the all zero path are representative distances. So all you have to do is take the first path, which is the all zero path. You will see 0 zeros written on top of it. It's called the all zero path. It's possible that one of the paths diverges, goes through ups and downs, and then finally remerges. Segment by segment, for these two segments, there will be some distance, Hamming distance. What is Hamming distance? The number of places the vectors are different. What are the vectors we are talking about? Whatever numbers you write, the vectors you write on the branch. Whatever is the output bits is what you write on the branches. We are talking about the number of places these vectors differ. So we go segment by segment. How far are these in terms of the Hamming distance? How far this segment is with this segment? How far is this segment with this segment? And so on and so forth. That will give me the distance between the two paths. Now you measure all possible distances between the pairs of paths. For a linear convolutional code, it is good enough to compare all possible distances from the all zero path. Whichever is the minimum is called the minimum free distance of the convolutional code. Let us look at an example. It is a 4-state trellis, 2 inputs coming, 2 bits come in, and so for every node you have 2 branches emanating out, and you also have written 2 bits on every branch, which depicts that 2 bits are thrown out for every input bit that comes in. Now from the all zero path, if you can see, zeros are written on all the branches, is the all zero path. We have been able to demarcate one particular branch which diverges and after some steps merges back. So if you calculate the distance, the Hamming distance between these two paths, 0 0 1 1 differ at 2 places, plus 0 0 1 0 1 differ at 1 places. So 2 plus 1 3 plus 0 0 1 1 differ at 2 places, plus 2. So 2 plus 1 plus 2, 5. 5 is the distance between all zero path and this path that diverges. You can carry out this exercise for all other pairs of paths. Whichever is the minimum, and incidentally whatever has been depicted forms a pair of paths which gives you the d free. So the d free for this convolution encoder is 5. Fine. Now let us talk about something called as Viterbi decoding. It was proposed by Andrew Viterbi. He was one of the founding members of Qualcomm. So this is one of the basic and popular techniques to do decoding for trellis codes. The objective is very simple. The objective is to find out the most likely path in the trellis. But clearly, if we keep track of all the paths, the number of paths grows exponentially as we move along the time axis. So there has to be a smart way to overcome this difficulty of retaining all possible paths. So the philosophy is as follows: an input bit stream comes in and we have to keep matching it branch by branch with the inputs that are written on top of the branches. So as we proceed, and we will see it through this example, we keep on defining a metric and keep track of so far what is the most likely paths possible. The other thing to remember is that the correct path that we are searching for must pass through a set of nodes. All paths pass through a set of nodes. So, identifying a certain path tantamounts to identifying the set of correct nodes. That means, we do not have to keep track of what are the correct paths if we can say what are the correct nodes. So, at each node we take a decision. For example, look at this node, there are two branches coming into this node. Clearly, only one will be correct. If we have a metric, if we have a measure to find out which is the more likely candidate, we only retain that and discard the other one. Thereby, we prune the search logically and optimally. This is based on the philosophy of dynamic programming, where you divide the problem into subparts and each subpart is optimally solved, so that the overall solution is optimal. So, let us look at the decoding algorithm. Suppose in the first step, the metric, in our case it is the Hamming distance between the received bit stream and the vector written on top of the branch. So, if you go back, suppose the received vector is the following 0, 1, 0, 0, 0, 0, so on and so forth, 1 and so on and so forth, and for the sake of illustration only, let actually the all 0 vector be sent, and there are a few errors being present. The ones represent the error. The question is, when we pass it through the Viterbi decoder, how does it get back to the original stream that was sent? So, if you go back, you see 0, 1, 0. Since there are 3 bits written on every branch, it implies that n naught is 3, 2 branches coming out from every node, so k naught is 1. So, it is a 1 by 3 encoder that we are talking about. For this one, if you see, if you look at the metric between the first 3 bits, because we will take 3 bits at a time, because 3 bits are written on every branch. So, the distance between the first branch and the first 3 bits received is 1, whereas between these 3 and the first 3 bits it is 2. So, my metric for the first 2 cases will be 1 and 2. If you proceed from here onwards, the next 3 bits are 0, next 3 bits are zeros. So, if you add to 1 0 metric, because no more addition took place, you still get 1. But here along this one, you have 1 1 1, but here the next 3 bits were 0 0 0. So, the metric goes up by 3. So, 3 plus 1 4 is what we will write here. So, this can be done mechanically for all the branches, and that has been shown in this example. Here 1 and 2 is what we got. Further metric was 0. So, 1 plus 0 is 1, but 1 on this branch we calculated it was 3. So, 1 plus 3 is 4 and so on and so forth. So, you can write the metrics for all, but we clearly not stop here. We continue this process, and very soon we encounter the third stage, where 2 or more branches, in this example only 2 branches, are converging at this place. We go back to our philosophy that correct path should pass through correct nodes. So, we must take decisions at a node. At this node, I have to choose between this one or this one, right? And here we can safely retain that branch which has the lower branch metric, fine, and discard the other one, because passing through that node, only that branch would be optimal which is so far optimal, and we continue this exercise beyond and beyond. So, we only retain those many paths that corresponds to those many nodes in a state, here only 4. So, the size of my memory which retains the number of paths does not increase exponentially, it is limited to the number of states. Now, we move one step forward and try to combine coding with modulation. As a specific example, we will talk about trellis coded modulation. However, you also have block coded modulation, which combines linear block codes with modulation. What is the reason for doing this? Well, so far we have seen that the encoder block, the channel coding block and the modulation block have been optimized separately. However, one of the objectives is the same for both: error correction or immunity to noise. Our different modulation schemes have been there to overcome the effects of noise as well. So, BPSK performs better in additive wide Gaussian noise than QPSK, for example. Right? There also the different modulation schemes have been designed that for a given power, what is the best noise performance you can get. Surprisingly, the objective of error control coding is also to overcome the effects of noise. So, in 1982, Ungerbock proposed combining the channel coding block and the modulation block together and optimize them together to come up with coded modulation. And it has been found that the performance of the coded modulation is better than separately optimizing coding and modulation. The other interesting philosophy is as follows: when you do error control coding, you add redundant bits. Redundant bits would require extra bandwidth. Question is, can I combine modulation, where I can play with the bandwidth requirement, and error control coding together, so that I can have an improved performance without spending more on bandwidth? It's like asking something for nothing, and TCM promises exactly that. You can get additional noise performance without asking for more bandwidth. So, traditionally coding and modulation have been considered as two separate blocks. Both these blocks, the encoder and the modulator, are optimized independently, even though their objective is the same, that is to correct errors introduced by the channel. Of course, modulation also has another purpose, to send the message across, but to do so without errors. It is possible to obtain coding gain without bandwidth expansion if the channel encoder is integrated with the modulator and optimized together. Consider data transmission over a channel with a throughput of 2 bits per second per hertz. So, basically we have to have 2 bits per symbol. The general idea is to take QPSK, because QPSK will take 2 bits per symbol and send it across. Given the signal to noise ratio, you will get a certain probability of error. The other possibility is to take 2 bits at a time and pass it through a 2x3 encoder, my convolutional encoder, right. So, now you already have some redundancy put in, because now you have one extra bit. So, for 2 bits you get 3 bits out, but we now do not use QPSK, but we use 8 PSK, which can take 3 bits per symbol. So, I did not ask for any extra bandwidth. Approximately QPSK and 8 PSK would consume the same amount of bandwidth approximately. So, what did we do? In the constellation diagram, if we are not going to expend more power, we have brought the constellation points closer together. So, by going from QPSK to 8 PSK, we have actually increased the probability of error. We know that. However, before doing that, we have already added some redundancy by using a convolutional encoder. Now, convolutional encoder will try to do error correction, thereby reducing the probability of error. Moving from QPSK to 8 PSK has brought the constellation points closer, thereby increasing the probability of error. If I have done my math correctly, then the advantage gained by coding will more than over compensate the loss that I encountered by moving my constellation closer. If that is true, then I can get performance improvement without increasing the bandwidth. If, however, I do not optimize properly, I might end up losing. So, the 8 PSK scheme yields the same information data throughput of the uncoded QPSK, but note that both QPSK and 8 PSK schemes require approximately the same bandwidth. It could be possible that the coding gain provided by the encoder outweighs the performance loss because of the 8 PSK sequence, and that is exactly done. It is doable, and trellis coded modulation can really outperform without asking for extra bandwidth. Now, you have, just like the free distance, which is actually the free Hamming distance in case of trellis codes, you have the free Euclidean distance. The definition is the same, but this time instead of Hamming distance, you are talking about Euclidean distance between two paths. So, you go for the various pairs of paths in the trellis, and that pair which gives you the minimum Euclidean distance is the D free for trellis coded modulation. Just like free Hamming distance is used to tell how good is your trellis code, similarly free Euclidean distance tells you how good is your trellis coded modulation. Fine. But one word of caution, convolutional codes are generally linear by definition. The construction that we do, we use linear adders and shift registers, so you end up making a linear code. On the other hand, the nonlinearity is introduced in the mapping process, because you are mapping the 3 bits, for example, to 8 PSK symbols. That is a nonlinear process. So, just going with the all 0 path may not give you the free Euclidean distance for TCM, but for linear convolutional codes, Hamming free distance is simply taken from the all 0 path. Here for TCM, you must consider all possible pairs of paths. Why is it called a convolution encoder? Well, if you look at the convolution encoder, it looks like a filter which performs convolution to the input bit stream, hence the name convolution filter. It is like an LFSR. Let us look at an example of a TCM. Here we have 4 states, but for every state you have 4 branches coming out. Clearly 4 states indicate that the 2 bits are present in the memory of the TCM encoder. However, 2 input bits are coming in, contributing to 4 branches coming out of every node. Now, for the output bits, we do not send them, we map it back to one of the 8 possible 8 PSK. So, in this example, 2 bits come in into the convolution encoder, 3 bits come out, but each of the 3 bits are mapped to one of the possible 8 PSK symbols. So, instead of writing 3 bit outputs on top of the branches, we write symbols. So, for any 2 bits that come in, a symbol goes out. We have combined the encoder and modulator. Now, if you want to find the free Euclidean distance, we have done the exercise, and these 2 pairs of path represent the minimum Euclidean distance. Here you can see that the all 0 path is not there. This is clearly not an all 0 path, this is not an all 0 path. So, it happens that the minimum Euclidean distance does not involve the all 0 path, because it is a non-linear code. All you have to do to find the minimum Euclidean distance is find the Euclidean distance between S0 and S7, S0 and S0, S2 and S1. From here, the sum total is the minimum Euclidean distance. It comes out to be 1.172 ES. Now, let us define something called as an asymptotic coding gain. it is a difference between the values of the SNR for the coded and uncoded scheme required to achieve the same probability of error. That is called the coding gain, usually defined for high SNR values. So, how much will I have to increase my signal to noise ratio in dB if I have to achieve the same bit error rate if I have no coding performance? So, uncoded, clearly uncoded will require a larger SNR, with coding you require a less SNR. So, you can trade off SNR for bandwidth, but here in TCM we have not even asked for extra bandwidth. So, if we define G infinity, the asymptotic coding gain, as 10 log d free squared over Es normalized coded divided by d free squared Es uncoded. Here G infinity represents the asymptotic coding gain and Es is the average signal energy. For uncoded schemes, d free is simply the minimum Euclidean distance between the signal points. Now, let us talk very briefly about mapping by set partitioning. So, the question is, how do you map? What is the best way to assign the 3 bits to the different symbols? How do you write symbols on the branches? If you go back and look at the trellis diagram, here part of coming up with a good code is to put certain symbols on top of the branches. So, question we are addressing is, how do we put these symbols? Why is this S0 and S7? Why not S4 or S3? Who decides the symbols? So, Ungerboeck, who had proposed TCM, had come up with one of his ad hoc techniques called the set partitioning. So, let us look at it. The mapping by set partitioning is based on the successive partitioning of an expanded 2 raised to the power m plus 1 array signal set into subsets with increasing minimum Euclidean distance. We will take an example. Each time we partition the set, we reduce the number of signal points in the subset, but increase the minimum distance between the elements. Mapping is done in such a manner so as to maximize the minimum Euclidean distance between different paths, right? Basically get the best possible d-free Euclidean. Let us look at the set partitioning of 8 PSK. So, the basic idea is as follows: keep subdividing it into smaller and smaller sets of points, but each time you subdivide, you increase the minimum Euclidean distance between the points. So, here I take the 8 PSK divided into 4 and 4 and then 2 and 2. For each step I increase the Euclidean distance. Now, if you look at a simple example, here is an example of a trellis with parallel paths, and Ungerboeck gave a set of 3 rules which says that you assign the diverging paths, right, from the lower sets so that the Euclidean distance is maximum. So, if this is S0 and S4, then you assign these two to the pair of diverging branches. So, here S0 and S4 for one diverging, S2 and S6 for the next one, and same for the merging back branches. So, what are the design rules? Rule 1: for parallel transition, if present, must be associated with signals of the subsets in the lowest layer of the set partitioning tree. We just saw how to do set partitioning, because these signals have the maximum minimum free Euclidean distance. Rule 2: transitions originating from or merging into one state must be associated with signals of the first step of set partitioning. All signals are used with equal frequency in the trellis diagram. These are ad hoc rules, but work well because there is no way we can know what is the best way to assign optimally all the symbols to all the branches in the trellis. So, it talks about the diverging branches, it talks about the remerging branches, it talks about the parallel paths, and tries to maximize based on only these three the maximum Euclidean distance. The TCM decoder is similar to the Viterbi decoder, but here the metric will not be based on Euclidean, it will not be based on Hamming distance, but it will be based on Euclidean distance, right. The task of the TCM decoder is simply to identify the most likely path in the trellis, and again we can use the Viterbi decoder to do the decoding part. Let us now summarize today's lecture. We started off with convolutional codes, which are codes with memory. We decided how to represent convolutional codes in the form of state diagrams, and then finally in the form of trellis diagrams. We learned how to encode using a trellis diagram as well as decode using a trellis diagram. We looked at the Viterbi decoding algorithm and did an example. Then we moved over to trellis coded modulation, which promises to combine channel coding with modulation to give me enhanced performance without asking for additional bandwidth, right. So, we will try to conclude our lecture here and look at certain other aspects of mobile communication in the subsequent lectures.